Once you get the hang of a related rates problem and you're able to dissect the text, they seem to be pretty easy. So let's give you some examples to help you on the way to that. How do I change slides? There we go. So let's read through this, dissect the text, and then we'll actually do the problem. If each edge of a cube is increasing at a constant rate of 3 centimeters per second, how fast is the volume of the cube increasing when the length x of an edge is 10 centimeters? So let's go through that at the beginning. So you can't really draw a cube that's increasing. So think of this as multiple cubes. So at the beginning, maybe the cube has a size 0. 1 second later, each side of the cube would be 3 centimeters long. After another second, each side of the cube would be 6 centimeters long. After another second, each side of the cube would be 9 centimeters long. And we want to know the growth rate of the volume of the cube right after this 9 centimeter part, right at 10. Okay. So I want to pull out a couple of things. Length x of an edge, that tells me how to label things. X, x, x is the diagram I'm looking at. Okay, let's go back and re-highlight this. If each edge of a cube increases at the constant rate of 3 centimeters per second, so we know that's, I don't know, plus 3 something. Well, that's definitely a rate, so we're going to have d something over dt. And that makes sense. So dt in the denominator, seconds in the denominator. Those both indicate a change in time. And, well, the length of an edge is x, so when each edge is changing, that's the rate dx dt. The rate of change of the side length x with respect to the change in time is always 3 centimeters per second. Okay. How fast is the volume of the cube increasing is the next thing we can pull out. Well, that's also a rate, so that's going to be d something over dt, because that's changing over time, and it's change in volume over change in time. That's our question. That's the answer we're looking for. Okay. So I suppose the last thing we can pull out is the moment we're talking about. That's not v, that's x equals 10. And so if you understand what all that means and you can pull all of those pieces out of the text, the rest of the problem is pretty easy. What I do want to point out is this 10 centimeters isn't always true. That's true for a moment in time. What I mean by that is it says that the edge of a cube is increasing 3 centimeters per second all the time. Which means for a moment the edge is going to be 10 centimeters, but that edge is going to keep growing and growing and growing. So what do we do next? Well, I'm going to get rid of this dv/dt where I want to write all my work. I'll write that off to the side. I like to write the rate I'm looking for so I don't forget later. So dv/dt is the derivative of a volume, so we need some equation that has a v in it. dx/dt is the derivative of some equation that has an x in it. So I guess I need some equation about a cube, in fact my yellow cube down there in the left corner, that has an x and a v in it. And of course the volume of any cube is side times side times side, so this cube has a volume of x cubed. So the next thing to think about, normally we wouldn't write this, but we're thinking of this volume equation having an input of time, and this side length representing some equation that when you put in the time you get the side length. So those two both have inputs of time, which is why when we take the derivative of this thing with respect to time, maybe I'll write that in the next line. So everybody knows that's watching this probably, dv over dx is x cubed, 3x cubed squared. Everybody but me. That's not the derivative we're looking for. That's the derivative of the volume with respect to the side length x. That's not what we're looking for. We're looking for change with respect to time. So we're not going to do that. We're going to take the derivative of volume with respect to time, the derivative of x cubed with respect to time, which means we're doing this stuff implicitly. So the derivative of volume with respect to time is just 1 dv dt. The derivative of x cubed is always 3x squared. But the d over dt tells us t is the input variable, which means x is the output variable of some function, x of t. So we're using implicit differentiation, the chain rule. So let's write that a different way. The derivative of something cubed is 3 times that something squared. Our something is a function x, which has a rate of change, dx dt. So let's go back and fill in everything. dv dt is what we're looking for, so we'll leave that alone. We can put the x equals 10 in now. And dx dt, we already found that up top. That was 3 centimeters per second. And so, out of room, dv over dt is equal to 900. And then what would that be measured in? Well, it's a change in volume over change in time, so centimeters cubed per second. If you're not sure how we got that, this 10 down at the bottom is 10 centimeters, and we're squaring that. This 3 is 3 centimeters per second, which means the units would be centimeters squared times centimeters over seconds. That's definitely centimeters cubed per second. Okay. All right. Let's go ahead and write our answer, but we're going to move on to the next page. So, when the length of the edge of the cube is 10 centimeters, the volume of the cube, I suppose we could say that, is increasing at a rate of 900 centimeters cubed per second. Is that the right number? Seems like it. That seems like a lot. Well, is that right? That seems like a huge number. So, earlier we had said that maybe at one point the cube had side lengths of 9, which would mean the volume of that cube would be 729 centimeters cubed. So pretty big, but this 900, this rate we got, is even bigger than that. So let's think about this. 1 second later, how big would the cube be? It'd actually be a lot bigger. That would be 12 by 12 by 12. And so we better get something huge. What's 12 times 12 times 12? Well, it's at least 144 times 10. So 1,728. Okay. So does that seem right? Well, now the 900 makes a little bit more sense. So in 1 second, from 9 to 12 side length, I know we were talking about 10, but 10 is at least near 9 and before 12. In 1 second, how much additional volume did this actually add? Almost 1,000 cubic centimeters. So this 900 that we found doesn't seem quite so crazy. Hopefully you realize the stuff that I wrote in yellow at the end here was just to help you. It's actually not the answer to the problem. I'm going to go on, dissect the text of another problem in 3, 2. All right, let's give you a chance to read this. All right, I assume you have. So a vertical cylindrical tank looks like that, and we need water flowing in. Water should be blue. We'll put an arrow to indicate flowing in. And let's go ahead and dissect everything. So how water is flowing into a tank at a rate of 5 cubic meters per minute. Okay, so this is plus 5 meters cubed per minute. And what could we call that? Water flowing into the tank, what sort of measurement would be measured in cubic meters? That would be a volume. So this is a change in volume over a change in time, dV over dt. Let's get back to yellow. The vertical cylindrical tank has a diameter of 6 meters. So I know how my students might screw that up. That diameter is 6, but usually we think of the equation for the volume of a cylinder, including radius, so I'm going to write that 3 as the radius. Now, it doesn't give us anything about a particular moment in time. How come? Well, unlike filling up a cone, the sides of the tank are all, well, that's not the right way to say it. In a cone, so as you start to fill up a cone, it fills up quickly at the bottom, or the height changes quickly at the bottom. That's because the sides at the bottom are closer to each other than higher up. So if we poured the same amount of water in, that might take a little less space higher up. And then if we poured even more water on top of that, that would take even less space. Okay? That's not the case in a cylinder. Any particular amount of water on the bottom would take up the exact same amount of space, oh no, higher up in the tank. Okay. So turns out that the depth of the water rising, or the rate at which the water rises, is going to be the same no matter how deep the water is. I suppose unless the tank is completely full. Okay. So, we have dV dt. This is supposed to be related rates. Can you find the other rate? Well, it does say rate. Find the rate at which the depth of the water is rising. So let's put our blue water back in. And, well, what would that be? So we want, good gracious. We know this is what we're looking for. How fast is that water rising? And that's a change, so it's going to be d something dt. That's my question mark. Well, we could call the height of the water above the bottom of the tank h, which would make this dh dt. Okay, so let's see if we can figure this out. Can you find some equation involving cylinders that has a volume and an h? So volume is pi times the radius squared times the height. Oh no. That might be a problem. We have 3 variables and we don't have a dr dt. Well, we don't have it directly, but we do have dr dt indirectly. Dr dt is the rate of change of the radius. Well, what's the radius of the, I don't know, the water inside the tank? It's always the radius of the tank. Since that radius is always 0, the rate of change of the radius, the radius is always 3. The rate of change of the radius is 0. That's going to come out in our equation anyways. So because the radius is constant, we can substitute that in ahead of time. The radius of the tank and the radius of the water are always the same. The height of the water in the tank is not the same, so we can't substitute that yet. We don't have that information either. So what's the derivative of volume with respect to time? dv dt. What's the derivative? 9 pi times the derivative of h with respect to time is dh dt. That's all I'm going to give you here. I think you can finish the rest.